Okay, so welcome back to now we will be talking about the effects of catalysts and enzymes on the speed of the reaction. So over here, what you will be learning is mainly the compound acting as catalysts in various industrial processes to really how it can actually help to save costs and to speed up the speed of the reaction. We also will be discussing some enzymes as biological catalysts to help us in our digestion. So mainly what's a catalyst? A catalyst tends to actually help to increase the speed of reaction by adding substance called catalyst. I mean, no, sorry. Catalyst is something that we can use to speed up the speed of reaction. Now, what is so unique about a catalyst is that by not only being able to speed up the reaction, they also remain chemically unchanged at the end of the reaction. Meaning, right, you just add one time, right, it will just keep on. It can be used. It can be reused again and again and again. Okay. So another some characteristics of these catalysts is that while it changes the speed of the reaction, it doesn't actually result in contributing to the other aspects of producing new products within the chemical reaction. This will actually be very good for us because when we want to actually create pure substances or to extract a particular compound, we will be able to manage it easily. And another thing is that because of the catalyst being able to be chemically unchanged at the end of the reaction, right? Only a very small amount is needed to help to speed up the speed of the reaction. They are definitely not used up during the reaction, and the same amount of catalyst is present at the beginning and at the end of the reaction. So when it comes to the physical appearance, right? Yes, it may change. That means basically if the catalyst is of a yellow color, you may result in your final reactants, right, to be your reaction, right, the product to become yellow color. Then you just have to extract out the catalyst only to get the purity. Okay, so how it actually works is for every reaction, right, there is actually a pathway. So this is one good example where the activation energy, let's say this is time and this is energy. Okay, the activation energy is basically the energy required, right, which is here, to start the reaction. So for the reaction to be started, right, you will need the amount of energy to overcome this hump first. And when it overcomes this hump, right, then the reaction will start to react. Okay, so what does that mean, right? It means that, right, over here, what we see is that for the catalyst, by adding the catalyst, how it's able to speed up the reaction is that it actually tends to lower this activation energy, this height. Meaning that you, rather than you require maybe 20 joules of energy to start the reaction, now you need maybe half the amount. So 10 joules you can start the reaction already. So this will actually help to speed up the reaction as it lowers the activation energy of the reaction. So it tends to be selective in its action and that different catalysts speeds up different reaction. Next thing is that impurities can also prevent it from working. So we tend to say that the catalyst is either poisoned or inactivated by the impurities. Catalysts and activation energies. So for catalysts, right, they tend to increase the speed of reaction by providing an alternative pathway of the reaction for it to produce. So just like how the original speed of reaction comes into this way, having an alternative pathway, you will have it here. And this would actually, the catalyzed reaction will then have a lower activation energy than the reaction without the catalyst, resulting in the reaction to actually occur at a faster speed. So for the catalyst reaction, more colliding particles possess energy equal to or greater than the activation energy. The frequency of effective collision will increase, resulting in higher rate of formation of the product particles. The speed of reaction will definitely be higher. One example is manganese 4 oxide, where it catalyzes the decomposition of hydrogen peroxide. So what it does is that we could see that so what we can do is that we prepare two test tubes with the same volume of hydrogen peroxide, and through this, by adding the same amount of the spatula of magnesium 4 oxide, we can actually test it out such that because it will produce oxygen gas, right? And for oxygen gas, it will tend to relight a um, it will actually be able to relight a glowing splint. So if let's say there is a glowing splint immediately, we could see that the 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 test tube with the catalyst helps to actually produce oxygen very fast. Whereas if you wait around like maybe a few more minutes, you'll see that this test tube A will also tend to light up, but it's slower. So the glowing splint at the mouth of the test tube with the manganese 4 oxide will rekindle and burn more brightly, indicating that speed of reaction increase in the presence of the catalyst. So another item to take note is how are these catalysts used in industry. It's like you can use iron to actually manufacture ammonia. You can use platinum or rhodium to actually use the catalytic converters that is found in your car engines to create cleaner air. You can have aluminum oxide or silicon dioxide for the production of hydrogen in the cracking process. This one we'll talk more in the chapter of organic chemistry. Another thing to see is actually enzymes. So enzymes are like what we have studied in our lower sex science. They are generally biological catalysts and they are protein in nature. In other words, right, these enzymes, right, they tend to act as biological catalysts to speed up the chemical reactions in our body or maybe in plants. And what happens, so in digestion, we tend to use enzyme. But one thing to note is how does it actually work is that enzymes, they tend to be very specific, meaning they only react to a specific type of reactant. They do not have one catalyst, one kind of enzyme to react with so many different kind of reactants. And what gives it that particular property is because of the shape of the active site. So for characteristics of enzyme, they are specific in their actions, like specific meaning, right? If let's say you have the enzyme and amylase, it will only digest starch into maltose and nothing else. It cannot, if you throw it with protein, you throw it to amino acid, amylase will not digest your protein, it will not digest your fats. So they only catalyze the reaction which changes starch into sugar, which is maltose in this case. And one good thing about enzymes is they tend to be very sensitive to changes in pH or changes in temperature. Why? Because enzymes, they tend to be helped by weak intermolecular forces of attraction. Sometimes there are some bonds there. And having too extreme temperature, like very high temperature, heat, will actually overcome these intermolecular forces of attraction. This will then result in the enzyme to denature as the shape of the active site has been deformed. Once it deforms the active site, it will not be able to catalyze the reaction, and therefore the enzyme is a bit useless. And definitely at too low temperature, there is a lot of inactivity of the enzyme. Maybe the enzyme is more clumped up, or there is actually very little frequency of collision between the enzyme and the particles. So this is another example. Sensitive to pH changes because if enzymes, they can also be helped by, I would say, uh, ionic bonds or electrostatic forces of attraction that involves charges for the compacting or the shape, the three-dimensional shape of the enzyme. So when you actually adjust the pH, you have the H plus and OH minus. This will disrupt the charges of the bonds found, the electrostatic forces of attraction within the enzyme, and this will then cause the enzyme to lose its active shape, active site, its conformative, and therefore the enzymes will again be useless. So where are enzymes used at? They can be used to manufacture wine or any other alcoholic drinks, such as the enzyme produced by yeast helps to convert your sugar, your glucose, into actually ethanol. So this is one such area where you can do fermentation. Next, we also use biological washing powder, meaning like if you stain your clothes, you need to clean off or wash off some of the food stain, right? You have modern detergent to contain enzymes that will help to remove stain caused by protein-based substance like your food and your blood. So it helps to digest and to break down those items. Okay, so overall we have already went through the speed of reaction. We talked about how to identify speed of reaction. We also went on to see how we can measure the speed of reaction, how the graphs can be plotted. We also did explore what are the factors that can affect the speed of reaction. We have the concentration of reactants, uh, pressure of the gaseous reactants, we have temperature, we have particle size, in which all actually influences based on the frequency of collision, effective frequency of collision, and therefore speed of reaction. And lastly, we also discuss about catalyst and how its role in terms of lowering the activation energy to create an alternative pathway for the reaction to speed up or to start with a lower energy cost. Secondly, we also talk about how enzymes can be used in our body or maybe in industrial purposes to help to actually speed up the reaction, and what are some of the factors like temperature and pH that can actually affect the efficiency of these enzymes. So that is all that we need to know for speed of reaction. Until next time, thank you.